Okay, folks, so we're moving along here. We've been talking about linear transformations, and now we're ready to talk about the linear differential operator. So let's suppose y lives in the space of Cn. What do I mean by Cn again? I mean that y can be differentiated n times, and that nth derivative is itself continuous. Okay? Then for the coefficient functions an, a1, a0, as long as those coefficients are continuous functions, then I can define a linear operator, an operator that takes a function y and does all of this to it. Okay? It's a little bit confusing, but what I'm saying is we can think of an nth order differential equation as a linear transformation. How does it behave? Well, it takes the function y. What does it first do to it? It takes the function y and first multiplies it by a0 of x. Then it takes y's derivative, multiplies that by a1 of x. Then it takes all the way up to y's nth derivative, multiplies that by an of x, and then sums all of those things together. And so it's doing a whole bunch of different operations on the function y. So I'm claiming that this is a linear transformation. We could do the proof for this. The proof of this is fairly messy, mainly because it's a lot of bookkeeping. You've got a lot of derivative terms to keep track of. You'd have a lot of factoring to do. And so what I'd rather do is show that this is a linear transformation by looking at one specific linear differential equation. In this case, we're going to look at the linear operator that does what to a function? It multiplies it by sine, then it takes the second derivative, multiplies that by 3, and then subtracts the former from the latter. Okay? So let's go ahead and show that this is a linear operator. What do we want to do? Well, we want to pick y1 and y2, and where do we want them to live? They need to live in the space of n times differentiable functions where that nth derivative is continuous. So we pick those two functions. Now let's go ahead and apply the linear transformation to them. So L of y1 plus y2. And let's remind ourselves of our goal. What's our goal? Well, our goal is we're going to work through this. You don't need to write this down. We're going to work through this. And our goal is to show that that's L of y1 plus L of y2. That'll show that the linear transformation distributes over this sum. Okay. Well, how are we going to do this? Well, we're going to apply the linear transformation. So what would that be? That would be 3 times d squared dx squared applied to y1 plus y2 minus the sine of x being multiplied to the sum of y1 plus y2. Now this part is fairly mechanical. I'm simply going to use my previously proved linear properties, do some distribution, and then recollect the terms. So notice I can rewrite this as 3 times, let's write it this way. We could go ahead after we do some distributing, we could rewrite this as 3y1 double prime plus 3y2 double prime minus sine of xy1 plus, minus sine of xy2. Now I'm simply going to regroup these terms together. This gives me 3y1 double prime minus the sine of xy1, grouping these, the first and third term together. And then I'm going to add to that, I'm going to add to that 3y2 double prime minus the sine of x times y2. And what is this expression right here? Well, this is what we would have gotten if we had applied the linear operator to just the function y1. So this gives me L of y1. Likewise, this is what we would have gotten if we'd plugged in y2 into our linear operator. So this is L of y2. And if you go back and look at our goal, yep, we've met that goal. We've just shown that that this particular second order linear differential operator can be distributed over the sum of y1 and y2. Okay, what else do we need to show? Well, we need to pick a real valued constant. So let's let alpha be just any old real number. And then we're going to look at the linear differential operator applied to a of y1. Well, that would be d squared dx squared of a y1. And I'm a little bit out of room here. I'll go scoot over. plus, excuse me, that should be minus the sine of x times a y1. Well, cleaning this up, this gives me a y1 double prime minus a sine of x y1, and I can factor that a out, and I'm left with y1 double prime minus the sine of x y1. Okay? If it feels like all we're ever doing is distributing and factoring, that's correct. That's all we're doing in these problems, but we're breaking it down to something that we've already proven in a previous course. So at this point, what have we shown? We've just shown that I can rewrite this as a times L of y1, because this expression right here is precisely what we would have gotten had we applied the linear operator just to y1. So we've shown that the linear operator distributes over sums and that constants factor out. That's enough to show that it is, in fact, yes, it is a linear operator or a linear transformation. Okay? Okay, so now we get into the idea of superposition, and I'm going to address that in the next video.